and part 2 begins. So I just talked about this octet rule. So let's look at how the octet rule impacts us here. So again, we'll look at the group number to see how many valence electrons, and then we'll see this octet rule, how it impacts whether what the valence, what we call the valence of these electrons are, or these elements are. So aluminum is in group number 13. So I said the last digit is the number of electrons, so I know that this is 3. And the question I have to ask myself is it easier to add 5 electrons to make this 8, or subtract 3 electrons to make this 0? And of course, it would be easier to remove 3 electrons. But what we have to remember is if I subtract electrons, I'm taking away negatives, so I make it positive. So the aluminum has a +3 charge. And don't ask me why, but chemists write it 3 plus. Go figure. Oxygen, on the other hand, oxygen, if you look at it, it's group number 16. So that tells us that there's 6 electrons in the valence shell. But then the question I ask myself, is it easier to add 2 electrons to make it 8, or subtract the 6? And of course, it's easier to add 2. So 2 becomes the number that we use. And since I've added electrons, I've made it more negative, so I get a 2 minus, -2 charge on the aluminum, or the oxygen. And then you may have looked at this in class and said we'll use this crisscross rule. So I'm going to sort of do this in red. So the crisscross, I bring the 3 down. It's right now it's a superscript. It's above aluminum, the way we wrote it down. I'm going to subscript it after the oxygen, and I'm going to take the 2 that's superscripted over oxygen and subscript that after the aluminum, and I end up with a formula that says that the aluminum, I've got 2 aluminums and 3 oxygens in aluminum oxide. Let me show you another sort of trick. It's a method that we can use for looking at this as well. So let's take this aluminum. So it's called the ball and hook method, and I quite like it. It's kind of visual. So the aluminum, we said it's got a the way to remember this is for elements we use a ball, and then when we talk about the valence, that 3 plus or the 2 minus, if it's a positive, we'll give it an up hook. So aluminum has a charge of +3, so it's going to have 3 up hooks. And then oxygen, again, that's going to be another ball, but oxygen has a valence of -2. So for every valence, the number that's up there, there's a hook, but these ones will be down hooks. And what I'm going to do is I'm going to hook the up hooks connect with down hooks, and then I'm going to have a stable configuration when all of these hooks are accounted for, that they're all taken. So if I look at aluminum has the 3 up hooks, oxygen has 2 down hooks, but those 2 hooks only hook up with 2 of the aluminum hooks. So I've got aluminum with 1 hook left over. Well, the aluminum only combines with oxygen. It's aluminum oxide. So the only thing I can do is I can add another oxygen. But that's got 2 hooks. One of them combines with that one that was missing, a down hook from the aluminum. But now I've got an extra down hook for oxygen. But again, oxygen only combines with aluminum in aluminum oxide. So I've got to add another aluminum atom. So that's going to have 1, 2, 3 up hooks. One of the up hooks combines with the down hook from oxygen, but I've still got 2 left over. Well, the good thing is if I add another oxygen with 2 down hooks, everything's taken care of. And then if you look at I've got 2 aluminum atoms, and I've got, or ions, because I've got these charges, and I've got 3 oxide ions. So my formula becomes Al2O3, which is precisely what we got with the crisscross method. But if this one works for you a little bit better, then you can work it that way as well. For the balance of these, I'm just going to use the crisscross method, and then we'll look at ways, if there's anything we have to any tricks that we have to remember with that. So let's look at magnesium. Magnesium, Mg, has a valence of 2 plus because it's in group number 2. Nitrogen, nitride, which is nitrogen, if you look, that's in group 15, so it's got 5 valence electrons. So again, it's easier to add 3, so it's going to be 3 minus. I do my crisscross, get the red, down and down, lose the charge. I mean the plus and minus, but just use the numbers. So I get Mg3 N2. So that's magnesium oxide, or magnesium nitride. This one here is a little bit interesting because this doesn't really follow in as an ionic compound. It is ionic, but it's what we call a polyatomic ionic compound because it's got a polyatomic ion, this hydroxide ion. Hydroxide is actually OH. And I'm hoping that you have this on your resource for the test, the exam. I know we've done it in the past. I'm hoping that it's going to be on the periodic table that Mr. Pandolfi gives you. But the hydroxide ion, it's a polyatomic ion that has a valence of -1. And just like when we write formulas, if the number is 1, we just don't write a number. We just say that it's negative. So a negative sign means that it's a charge of -1. And then we look at lithium. Well, lithium is it's a metal. It's a group 1 metal. So it's going to have it's got 1 valence electron. Of course, it's going to end up with a charge of +1, or I'll just use plus. And then I use my crisscross method. Well, there's nothing really to crisscross because there's only ones, but they come down and we don't write the ones. So we end up with LiOH is lithium hydroxide. And so that's how we write these formulas. So let's try some more. We're going to use these. These are not what I would call polyatomic ions, with the except the last one, with the exception of the last one. I'd refer to these more as what are called multivalent ionic compounds. And this is when we start to deal with metals. So these ionic compounds are generally, well, not generally, they're always, as far as I know, we've got a metal combining with a non-metal. But when we look at a periodic table, there are metals and then there are metals. So if I look at the far left of the periodic table, the alkali and alkaline earth metals, these first two groups over here. So group 1 and group 2, these are very strong metals. They're highly reactive, and they are very rarely found alone in nature because they're so reactive. The thing is, though, as I get it, and you see there's kind of a gap in those first 3 periods of the periodic table, those first 3 rows, and there's a large gap, and then we go down to the 4th row of the periodic table, the 4th period and below, and then in that gap we've got these other metals, and we call these metals, these are called transition metals. And transition metals are metals that can be found often on their own in nature, but they also have these sort of weird electron configurations where, again, without getting into the details of the sort of smaller details of electron structures around atoms, the bottom line is they can form these ions, and this is where, if you look at the key in the periodic table, it says here that there's a common ion charge, and then there's other ion charge, and there might be a couple of other ion charges. But or I guess most often, iron will form an ion by losing 3 electrons. But sometimes it can form an ion by only losing 2 electrons. So it can have a charge, when it becomes an ion, it can have a charge of +3, or it can have a charge of +2. Now both are possible, and both do happen often in combination with other elements. And moreover, it can happen
I can get iron can form these +2 ions when combining with a non-metal, but they can form +3 ions combining with the same non-metal given the right conditions. So it gets a little bit tricky there, but there's a way to deal with that. So let's look at these ones here. I've got this one here in particular shows how iron will make these form these multivalent ions. So here I've got iron combining with chlorine, so it's going to be iron. I'm going to leave a bit of a space before I write chloride, and you'll see why I do it in a second. So it follows the same rules as before. We say iron is the metal, and followed by the non-metal chlorine, which I change, and I change the ending of chlorine to chloride. But the thing is, I know I have to sort of again take a look at this. I'm going to kind of reverse engineer the formula and figure out what the valences of these ions were when they combined. Well, chlorine, if you look at the periodic table, only forms a -1 ion. Iron. So if this was if this FeCl2 was the chemical formula, then iron, if I undo the crisscross method, it had to have had a charge of +2. Right, because the 2 went down to form the formula, the 2 had to go back up to as the valence to start with. So it had a charge of +2. So, but again, we look at the periodic table, and that's a possibility. It can be +2 or it can be +3. So what I know is in this particular formula, it must have been the +2 iron ion that formed. So we say that the way we denote that in our formula name is we put in Roman numerals after the metal. We say it's iron 2 chloride. So that's the standard way of doing it now. There was an old way of doing it that would be called ferrous chloride, but you don't have to worry about that. That's no longer the standard that you have to work by. If you take grade 11 chemistry, they'll probably teach you that, but for the purposes of this course, you don't have to worry about that, the older way of naming these things. So let's take a look at this. I've got FeCl3 this time. So again, let's sort of reverse engineer it. I'm going to have Fe and Cl. I know that the ionic charge on chlorine, on the chloride ion, is -1. But then if it's FeCl3, then this particular iron ion had to be my +3 ion, or my +3 ion. So again, it's a possibility. I look at the periodic table. It can be 2 or it can be 3. In this case, it must have been the +3 type of ion that formed this compound. So again, I'll write the name. So it's iron. I'll leave some space. Well, we can, using the same rule. Again, it's Roman numerals. So I write iron, Roman numeral 3 in brackets, chloride, because that Roman numeral tells me which valence of that transition metal that was used to form this compound, or the ion that formed in the making of this compound. And just to recap, Roman numerals are for Roman numeral 1, if it's a 1, which is possible, we use I. Roman numeral 2 is II. Roman numeral 3 is III. Roman numeral 4 is IV. You wouldn't need any. So this is 1, 2, 3, 4, and you wouldn't see any of any metals that would form anything. I don't think I can't recall a 5. If there was a 5, it would be V. I don't think you'll use that, but okay, I'm coming up on 14.5 minutes. This is part 2, and I'll save this and record part 3 again in a few more minutes.